Have you ever wondered what mysteries the universe holds beyond what our eyes can see? There's a vast expanse out there, brimming with enigmas and wonders that stretch our understanding and challenge our perceptions. Every star that twinkles in the night sky, every nebula that paints a celestial canvas holds a story of cosmic proportions, of time and space, of life and death, and of the incredible complexities that exist beyond our earthly realm. Among these celestial wonders, there exist phenomena that are astoundingly intriguing yet elusive. One such marvel is the Pulsar wind nebula. These are cosmic entities born from the remnants of massive stars in the heart of the universe's most extreme environments. They are a testament to the power and grandeur of the cosmos, hiding in plain sight, yet demanding a keen eye to truly apprehend their essence. Dive with us as we unravel the mystery of Pulsar wind nebulae. To understand Pulsar wind nebulae, we first need to acquaint ourselves with neutron stars. Neutron stars are the city-sized remnants of massive stars that have exhausted their nuclear fuel reserves. When a star, much larger than our Sun, reaches the end of its life cycle, it goes out with a bang in a massive explosion known as a supernova. This catastrophic event blows away the outer layers of the star, leaving behind a dense core. The gravity of this core is so intense that it crushes the remaining particles together, creating a neutron star. Now, let's talk about their size and density. Despite being only about 20 kilometers in diameter, roughly the size of a bustling city, neutron stars are incredibly dense. Imagine squeezing a mass up to twice that of our Sun into a sphere no larger than a city. The result is a star so dense that a single teaspoon of its matter would weigh about 1 billion tons on Earth. Neutron stars also have another remarkable characteristic: their rapid rotation. After the supernova explosion, the conservation of angular momentum causes the remaining core to spin at an incredibly fast rate. Some neutron stars can rotate hundreds of times per second. This makes them some of the fastest spinning objects in the universe. But what makes these neutron stars truly fascinating is their intense magnetic fields. These magnetic fields are 1 trillion times stronger than Earth's and cause beams of radiation to emanate from the poles. As the star spins, these beams sweep across space like a cosmic lighthouse. When this beam points towards Earth, we detect a pulse of radiation, hence the name Pulsar. These fast-spinning neutron stars, also known as pulsars, play a crucial role in the formation of Pulsar wind nebulae. But that's a story for the next scene. Stay tuned to delve deeper into the cosmic winds that shape the universe. Now that we know about neutron stars, let's explore how Pulsar wind nebulae come into existence. A pulsar, essentially a rapidly rotating neutron star, is a celestial object that emits pulses of radiation at regular intervals. These pulses are a result of the star's intense magnetic field and swift rotation. Now, as these pulsars spin, they release a steady stream of high-energy particles and magnetic fields. This release is known as the pulsar wind. This pulsar wind is not like the wind we experience here on Earth. It's an outpouring of charged particles, moving almost at the speed of light, propelled by the pulsar's rotational energy. This wind, carrying along with it the pulsar's magnetic field, flows out into the surrounding space, creating a bubble of high-energy particles. Now let's imagine the pulsar at the center of this expanding bubble. Like a lighthouse in the middle of a stormy sea, its beams sweeping across the cosmos. Around this pulsar, the pulsar wind slows down as it moves away from the star and begins to interact with the slower-moving material around it. This interaction creates a shock front, a place where the fast-moving wind abruptly slows down and where most of the wind's energy is converted into heat and light. This shock front is where the magic happens, giving birth to what we call a pulsar wind nebula. The high-energy particles caught in the shock begin to radiate, lighting up the nebula and creating a visible structure around the pulsar. The nebula grows as the pulsar continues to emit wind, acting as a sort of cosmic lighthouse beacon, visible even across vast cosmic distances. So the Pulsar wind nebula is essentially a cosmic weather system created by the interplay of high-energy particles, magnetic fields, and the rotation of a neutron star. It's a testament to the incredible energy and dynamism of the universe, a dazzling light show powered by the spinning core of a dead star. The Pulsar wind nebulae, therefore, are born from the winds of rapidly spinning neutron stars. The formation of pulsar wind nebulae is just the beginning. They possess a structure as intriguing as their birth. Let's dive into the intricate structure of pulsar wind nebulae, a marvel of cosmic architecture. This structure is generally divided into three main zones: the termination shock, the wind zone, and the nebular zone. The innermost region, closest to the pulsar, is where the termination shock resides. This is the area where the pulsar's wind, a stream of highly energized particles, abruptly slows down upon colliding with the surrounding interstellar medium. Imagine a boat swiftly cutting through water. The termination shock is akin to the sudden deceleration when the boat hits a wall of dense fog. Beyond the termination shock lies the wind zone. This area is marked by the pulsar's wind expanding outward, much like a cosmic windmill. The particles here are still highly energetic, but they gradually lose their speed as they move away from the pulsar. It's a realm of constant change where high-energy particles from the pulsar gradually transform into the slower-moving particles of the nebula zone. Finally, we reach the nebula zone, the outermost region of the pulsar wind nebula. Here, the particles have lost most of their initial energy and have slowed down significantly. Yet they still retain enough energy to emit the beautiful, often multicolored glow that makes pulsar wind nebulae such a sight to behold in astronomical images. Each of these zones interacts with the others in a constant dance of energy and particles. This complex interaction, driven by the pulsar at the heart of the nebula, helps shape the nebula's overall structure and appearance. So, while they may seem ethereal and distant, pulsar wind nebulae are actually dynamic and ever-changing structures. They're a testament to the incredible forces at work in our universe, constantly shaping and reshaping the cosmic landscape. This intricate structure makes pulsar wind nebulae a fascinating object in the cosmic world. These cosmic structures are not just intriguing, but they also hold significant value for the scientific community. Pulsar wind nebulae, these ethereal cosmic chandeliers, have a lot more to offer than meets the eye. Their study holds the key to understanding some of the universe's highest energy phenomena. Picture a pulsar wind nebula as a colossal natural particle accelerator, ramping up particles to energies way beyond what we can achieve with our earthly contraptions. As these particles speed through space, they collide with light and other particles, creating gamma rays. These are the most energetic form of light, and pulsar wind nebulae are among the universe's most prolific sources of these gamma rays. Observing and studying these gamma rays helps us unravel the mysteries of high-energy processes in the universe. It's like having a front-row seat to a cosmic fireworks display that not only dazzles but also informs us about the universe's fundamental aspects. But that's not all. Pulsar wind nebulae are also instrumental in our understanding of cosmic rays. These are high-energy particles zooming through space at nearly the speed of light. For over a century, scientists have been trying to figure out where these cosmic rays come from and what accelerates them to such high speeds. The answer, or at least part of it, lies in the pulsar wind nebulae. When a pulsar releases a wind of particles and energy, it creates a nebula around it. This nebula acts as a cosmic accelerator, propelling particles to near light speed. By studying the pulsar wind nebulae, scientists can learn more about the nature and origin of cosmic rays. In a nutshell, pulsar wind nebulae are like cosmic laboratories, brimming with clues about the universe's high-energy phenomena. They help us comprehend the nature of gamma rays and cosmic rays, shedding light on the fundamental processes that rule our universe. The pulsar wind nebulae, a cosmic spectacle, serve as a window into the universe's high-energy phenomena. Our journey to the core of pulsar wind nebulae has been enlightening, hasn't it? We've voyaged to the heart of neutron stars, where the intense gravitational pressure gives birth to pulsars. We've seen how these pulsars emit streams of energetic particles, creating the cosmic winds that form pulsar wind nebulae. We've marveled at the intricate structure of these nebulae, with their nested shells of emission and their mesmerizingly beautiful yet deadly jets. We've understood their significance, how they help us understand the life cycles of stars and the very nature of the universe itself. We've come a long way, my fellow cosmic voyagers. But remember, every answer we find only leads to more questions. Such is the nature of our universe, a never-ending sea of mysteries with enigmatic phenomena like pulsar wind nebulae stirring its depths. As we conclude, remember that the universe always holds more mysteries for us to unravel, like the enigmatic pulsar wind nebula. So keep exploring,